Welcome to this session about SPSS. This is a follow-up for session 7 to 8. Previously, we had discussed the how to do the bivariate analysis using the independent t-test, the pair t-test. We also talked about correlation. Then we also addressed the ANOVA, when the groups are independent and when the groups are dependent. Okay. What we will cover in this lecture is the simple linear regression. First, let me give a short description of what's the idea behind simple linear regression. Like in the correlation setup, you're going to have an y variable. So basically, your y variable is your dependent variable, your outcome variable, and an x variable, which is it's your independent variable. And both of them are numerical in nature. This is the idea behind it, but they don't have to be one outcome, one exposure. There could be any two variables, and you want to see the relationship like we did in the correlation. And if you remember in correlation, we talked about you could create a scatter plot, and so forget about this line over here. Scatter plot would be just dots. And if you see something like that, as we said in the Pearson correlation, you try to see how much correlation there is between the x variable and the y variable. And a Pearson correlation just tries to quantify this relationship, and it will produce a value between -1 all the way up to +1, where 0 indicates no correlation. A +1 indicate a perfect direct correlation, and a -1 indicate a perfect negative correlation. What we will do in a linear regression is, in addition to that, you're going to try and fit the best line that accommodates all the points. Okay, so you're trying to create a line, and if you remember from your maybe school courses, a line has the following form: y is equal to, so maybe some of you know it as ax plus b. Okay, and what matters here is that y is the value on the y-axis, so if this is your dependent variable. X is your value on the x-axis and your independent variable. So x is independent, y is the dependent, and a is what is said to be your slope. Basically, this is by how much y will increase for every unit increase in x. Okay, so if you pick any x, so this is x, if you go up 1 unit, so that would be x plus 1. If you go back to your line, you will notice that you went from this point here all the way to that point. So your y used to be here, and now your y is over there. So the increase from here to here, this is your a. Okay, this is called the slope. And finally, b is your intercept. So if you extend the line till it crosses the y, so this is the value of y when x is equal to 0. When x is equal to 0, all of this disappears and you're left with b, and this is your intercept. Okay? So a linear regression like the one I'm trying to explain now, this is where you try to fit a line that has the best fit for the data. Okay, so let me just clean this up again. And so one more time. You have your x and you have your y. Okay, so this is your y and this is your x. You plotted your values. Okay, and then you're trying to find a line that has the best fit. Okay, someone might ask me, like, why this line and why not all that line? What makes the first one better than the second one? Actually, the way statisticians find the best line is that what you're going to do is you're going to calculate the errors, basically the errors in the distance from the actual point. So this is the actual point, and then if you go down to the line, this is the um, estimated value. Okay, so that distance is considered to be your error because you're estimating the value to be here, whereas the reality of the value is here. So you try to find all the distances, okay, from your actual value to the ones that you predicted or you estimated, and the line that produces and you sum them up, you sum these values. The line that has the lowest sum, the lowest sum of these distances is your best line. You might have noticed that some of the distances are above the line, some of the distances are below the line, and producing errors that are negative and positive. We square the error to get rid of that, and we find the least squares. Okay, so the method is called the least square. Try to minimize the squares as much as possible, and that would be your perfect line. All right, so long story short, SPSS would do all of this for you, and SPSS would come up with an output stating that the value, so remember the line has this form. Let me change the color. It has this form where y is equal to ax plus b. You better start getting used to a different format of writing the formula. So we're going to write it as y equal. The intercept is called b0. So we start with the intercept. And then for this one, we're going to call it b1x. Okay? So all the values that are part of the formula are going to be called b. And it's b0 for the first one, that's the intercept, and b1 for this variable. The reason I called it b1 because later on you will see that I may add another independent variable. So I may add another independent variable called z, and that will have also an intercept, a slope, and that slope will be called b2 or beta 2. Okay, and I may add a third one, and so I will have a beta 3. Maybe your third independent variable is called t, for example. Okay, so each of your independent variable will have its own slope. Okay, and that's how we write the formula. So what SPSS is going to do, SPSS is going to give you these coefficients. Okay, that's what SPSS will do. It will produce these coefficients. So let's start simple. Let's start with the simplest linear regression, and that's where you have a simple linear regression, meaning you only have your y variable and your x variable. And when you try to find a linear relationship by Newton, linear correlation, you can create a line that will have the format that I talked about: y equal beta 0 plus beta 1x. Okay, and an SPSS will produce all of this for you. So the statistical significance will come by testing if this slope really exists or not. So the null hypothesis will be that the slope in for x, okay, so the real value of beta 1. So beta 1 in the population, so بس حتى نتذكر إنه we always test using the population value is equal to 0. That is going to be a null hypothesis. So remember, if the slope is equal to 0, it means you do not have a line that either goes up or down. So you have a flat line. This is your null hypothesis. And SPSS not only is going to produce your estimated beta 1, but it will also produce a p-value for that to test if it's statistically significant. All right? And we will see all of this in a minute when we run the analysis. trying to remember if I want to say anything else about the testing hypothesis. Let's do the example and see if it comes back to mind. So I will open the data set that we've been using so far for this, where you have the gender, you have the medicine, blood pressure 1, blood pressure 2, and blood pressure 3. As a reminder, gender has two values, 1 and 2, and medicines has three values, the 1, the 2, the 3, and blood pressure 1, blood pressure 2, blood pressure 3. You may remember previously that if you do a correlation, okay, so if you put your three blood pressure together, and if you try to do a correlation among them, you get a correlation matrix like this one, and you can see that blood pressure 1 is not correlated to blood pressure 2, and blood pressure 1 is not correlated to blood pressure 3, and blood pressure 2 and blood pressure 3 are not correlated as well. Nothing is correlated. Okay, let's just let me go back here. All right. So if I go and I do, if I go to regression and I pick linear regression, so in the dependent variable, you're going to put your y variable. So here I'm going to put blood pressure 3 as my dependent variable, and I want to know if it correlates to blood pressure 1. I've already answered the question when I did the correlation. So I'm going to ask the question if I can fit a line. Alright, so let's see if I'm going to pick anything from here. For statistics, I want the estimate, the model fit, descriptives, maybe I want the descriptives. Okay, continue. For plot, no, I don't want anything of this as of now. Okay, I think it's enough. I don't think I need anything more sophisticated than that. So just click OK. Alright, so here's your regression. You get first a descriptive table where it shows you the mean of every variable and the standard deviation and the number of variables for each one of them. You also get a Pearson correlation automatically, which should be exactly the same value we had previously. Okay, so the Pearson correlation between blood pressure 1 and blood pressure 3 is negative 0.125. We have a negative correlation, and the p-value for that is 0.227. It's not statistically significant. So let me go back to the Pearson correlation here. Blood pressure 1 and blood pressure 3, if you look at them, the Pearson correlation is negative 0.125, exactly what we had, and the significance is 0.455. It's not exactly the same because it's doing a one-tailed significant and not a two-tailed. If you multiply the one-tailed significant by 2, you would get the exact same p-value we had above. All right. Next, what you're going to get is your model summary with the R, which is exactly your correlation, but it's a positive, and then you get an R square. I will talk about the R square in a minute. Then you get an Anova table. Again, though we're not running an Anova, we're just running a regression, but you will see it's different because this time the Anova has regression. So what it's doing, it's testing if the regression has anything statistically significant in it. And if you look at the degrees of freedom, you have 1 degree of freedom because you're only fitting one X in the model. Later on, if you try to add another X in the model, this will become 2, but you only get one p-value. So this is an omnibus test if any of your independent variable is statistically significant or not. Sure enough, if you look at the p-value, 0.455 is exactly p-value we get when we're doing the correlation because you only have one variable. So when you have only one X correlated with one Y, the p-value for the correlation is exactly the same than the p-value for running a regression for the Anova. And even when you go down to the table that is going to produce your coefficients, yani beta 0 and beta 1, you will see you'll get the same p-value. So down here you get your coefficients. First you have the constant meaning this is the intercept. So the intercept is 144.7, with a standard deviation of 22.25, and you get a p-value for that, but we don't really care for the p-value for the first one. The second one is your beta for blood pressure 1. Yani this is the slope for your x variable. Remember, your x variable was blood pressure 1. This is the slope, negative 0.125. And if you look at the p-value of that slope, it's 0.455, exactly equal to the p-value for the ANOVA, exactly equal for the p-value of the correlation. This is because you have only one x variable. When you have only one x variable, so let's recap all of this. If I'm trying to fit one, so if I have the situation where I have y and x and I'm doing the scatter plots, okay? So in this instance, if you calculate a Pearson correlation, that Pearson correlation will have a p-value, okay? So this is one analysis. Another analysis, you try to fit a linear model, and that linear model will produce first an ANOVA table that will have a p-value. This ANOVA table is testing whether any of the axes is statistically significant. In this instance, you only have one x variable, and therefore this p-value is going to be exactly equal to this p-value right there. Also, you're going to get the values of the intercept and the value of the slope, and the p-value for the slope is going to be exactly equal to the p-value of the ANOVA, which is exactly equal to the p-value of the correlation. All of this because you're fitting only one x variable. So your model will look like in the example we did, blood pressure times 3 is equal to the intercept, which was 144, I guess, minus the slope, which was 1.25, I think, times blood pressure 1. Now, this is the model. However, since this intercept was not statistically significant, I have to drop it from the model. And what you're left with is just this, the intercept. And usually in that instance, the intercept, when you have nothing here, that is going to be your average of blood pressure 3, because that's the best uh, representative of blood pressure 3. I hope this is making sense. Um, I wish we had an X variable that was statistically significant to show you. What I'm going to do is I'm going to repeat the linear regression model, okay? And I'm just going to throw blood pressure 2 here, okay? So this time what I'm doing is I'm having two independent variables trying to predict the outcome. So again, you have an R, but this is an R for both P2, P1 at the same time. وفي عنا R square, and I need to explain what the R square. Notice how now your ANOVA has for regression degrees of freedom 2, because you have two independent variables, but it's not statistically significant. So this is an omnibus test. This is testing if any of the two independent variable is statistically significant. So just by checking that the ANOVA is not statistically significant, you can know that your when you go down to the slopes, that neither of the slope is going to be statistically significant. And sure enough, when we look at the coefficient table, you have your intercept equal 107. Your slope for blood pressure 1 is negative 0.102, and it's not statistically significant. The slope for blood pressure 2 is 0.249, and it's not statistically significant. Neither of blood pressure 1 nor blood pressure 2 has a statistical significantly coefficient that correlates it to blood pressure 3, and therefore both of them are not a good X variables, or not good predictor of your blood pressure, and therefore they should be removed from the model. So I ran them anyway, just to show you how you can get these two, although the ANOVA is only one. Final word. So what is this business about R square? R square, as I mentioned previously, this is the coefficient, Pearson coefficient that is squared. So you take the R and you square it to get the R square. And basically, this is, you can turn it into a percentage. And the way you interpret it, you say that this is the percent of the variability in Y that can be explained by X. So for instance, if the correlation between X and Y came out to be equal 0.5, meaning the R square is 25%, you would say 25% of the variability in Y is due to X. So for example, if in our situation Y was blood pressure at time 3 and X was, for example, BMI, you would say that 25% of the variability at for blood pressure at time 3 is attributed to BMI. The way we calculate R squared, as I said, is using the correlation and you square it. This is true in a simple linear regression. Simple linear regression meaning you only have one X in the model, but the one X. When you start to have more than one X, it becomes harder, but you can still get to it. If you go back to your table and to your ANOVA, you can still get to this R square by taking the sum of square of the regression and you divide it by the total sum of square. So we say this is the total sum of square that was explained by the regression model out of the total sum of square, and that will give you the R square in this table right here. So next we're going to look at what if your X variable was not numeric, how do you deal with it?